Alright, let's take a look at sample problem 1010. We've seen this configuration before, but we just maybe had like a mass attached to this pulley. But in this case, we're not using this as a pulley. This cylinder right here, or uniform disc, I think we should label it. Uniform disc. Has some moment of inertia. It has mass. So it's not going to spin freely. We've always said that suppose the pulleys are frictionless and massless. Well, in real life, they have mass, and it actually, if I release this system from rest right here, it's gonna accelerate slower if this thing right here, the disc, has mass versus if it doesn't. Okay, so let's take a stab at this. If we looked at this mass right here, first of all, we have a tension going up and mg going down. We can Newton's second law it and say the tension, the summation of the forces, is equal to the mass times the acceleration. And it's a tension going up and an mg going down. That does not equal 0. Remember I taught you that. It's going to equal some mass times acceleration. Let's hold on to that for now. And then, well, let's use the new equation for rotations. Newton's second law for rotation, which says that if we have a torque, it's going to equal some I alpha. Now, they didn't give us what I was, but they did tell us the mass in this problem. They said it's a uniform disk, so we can calculate I with looking up in a table. I is 1/2 mr squared for a uniform disk. And we can just throw that in there. We get a torque equal to 1/2 mr squared times alpha. Don't forget that alpha. And then for the torque, torque is just equal to the perpendicular distance times the force, right? Well, we have the distance right here. It's r. And we know what the force is. The force is equal to the tension, right? That's exactly how hard it's pulling down is equal to the tension. That's why we needed Newton's second law for particle motion. And now we're looking at the rotation of a solid body. We'll call that equation 2. Now we can put these together with the fact that the acceleration of any point is equal to r alpha, right? If we draw another circle, if this thing is spinning, which it would be after we released it, it might have some alpha, and that's gonna relate the radius to whatever the acceleration is at this point. By the acceleration is equal to r alpha. And using that in these two equations, we can figure out that the acceleration is equal to the acceleration of gravity times 2m over m plus 2m. And if you wanted to know what alpha is, you take this and put it over r. Alpha is equal to the acceleration over r. So take that whole thing, put it over r. And we've now described the motion of a point on this, or how fast it is accelerating in the angular direction.